In this video, we're going to get to build our model and finally test the association between our exposure variable and our outcome variable. So I'm here in my SAS program, and the first thing that I want to do is I want to create a live name statement that I can use to bring in my working data. So I'm going to go to my folder, and here is the working data folder. And so this is where all of my create working data SAS programs are. And here's my working data. So I'm going to grab the address here, and I'm going to create a live name statement for that. Live name, and I'm just going to call it D for data. And then I will put in the folder there. And now I'm going to save this. And this is going to be my analysis SAS code. So I've created a new folder here called analysis, and I'm going to save it in here. I'm going to call it analysis version 1. So we'll save that. And I also want to have open my last SAS program, or the highest version number of my working data SAS program, so that I will be able to reference the variable names there that I need. And also, if I want to do any additional changes to the variables, I can do that in the create working data SAS program. So I'm going to go up here to view, and I'm going to view a new enhanced editor. And then I'm going to open in that, I'm going to open up my highest version create working data, which for me is version 5. So I'll have these two windows. I'll have the analysis program, and I'll have the create working data program. I don't need to run the create working data program right now because I've already run it, and the version of the data, the working data that I'm going to use is right here. So I'm actually going to grab the name here, hit the rename, and then control copy. And then what I can do in my analysis program, I can say data, work data, and then I'm going to say set D, and then I'm going to grab that working data, and I'm going to run this. Now let me save it, and let's just run it and see if it grabs the data. So it grabs the data. It has 20,015 observations. You might remember from the previous video that these are all the individuals in the 2007 and 8 and the 2009 and 10 data who went to the Mobile Examination Center. And they all have to be in my data set because that's the group of individuals who are associated with the weight variable that I'm using. I'm using the MEC 2-year weight variables. I've converted them into 4-year weight variables by dividing by 2. That's in the previous video. So if I look again at my include variables, I had 2 of them. One was called include FEV, and the other was called include COPD. Or was it called include FEV1? Let's see if this runs. Oh, didn't run. I think it must be include FEV1 here. Let's try this. Yeah, that was it. So we have, for my FEV1 model, I'm going to be able to use 7,072 individuals. For my COPD model, I'm going to have 7,338 individuals. These other individuals are either out of the age range or they have missing values on some of the variables in my model. So I'm going to start with the FEV1 model. That's going to be my linear regression model. And then after that, we will do the logistic regression model. So I'm going to get rid of this. And so in this data and set statement, I'm taking the working data from my computer's hard drive memory and putting it into the working memory of the computer, the temporary memory, and calling it work data. So I'm just going to work in that. So I'm going to call that set work data. And so now we're ready to build the model. So this is a linear regression model. Now, if you are doing a regression model from a data set that didn't have a complex sampling design like the NHANES, ordinarily we would use a procedure called procreg. That's the ordinary one that you would use. And for logistic regression, we would use proclogistic. But since we have a complex survey, we're going to use a different procedure for these. And for the linear regression, it will be proc survey reg. And for the logistic regression, it would be proc survey logistic. So these are the procedures that we're going to be using. So we'll come back to survey logistic later. So in proc survey reg, we have some statements that we have to put in here for the complex survey. And they are strata, cluster, weight, and domain. And the variables for strata and cluster, these were the ones we took out of the demographics data set. And there are these two that we put at the end here. One of them ends with PSU and the other ends with STRA. So I'm just going to grab these two variable names from here. And I'll put them down here. So the one that ends with STRA, that goes after strata, and PSU goes after cluster. And these are just related to, they mark how particular individuals were sampled in the complex survey design. If you want to understand that better, you can go to the NHANES website and they explain it in detail there. Now, the weight variable is going to be the 4-year weight that we calculated. And we calculated it down here towards the bottom. So I called it weight MEC 4 years. So this is the variable that I want to put in the weight. So yours will be the weight variable that you calculated. And the domain here, this is the variable that we created, the include variable. So this marks the individuals who we want to include and not include in our model. And mine was called include FEV1 for the linear regression model. So we have to have this strata, cluster, weight, and domain. We have to have these 4 statements in order to correctly model our data from the complex survey design. So the next statement is our model itself, and the command is model. And so it's kind of a shorthand version. None of the betas are listed. None of the plus signs are listed. They are just assumed. And so the way we write it is first we write the outcome variable. And my outcome variable is the FEV1 to FVC ratio. I'm going to go over here and find my variable name. So here it is, the FEV1 to FVC ratio. And then we have an equal sign. And then we put our exposure variable plus all of the covariates that we want to be in the model for conditioning in order to control confounding in the model. So I want to grab the variable for my exposure. So I'm going to come over here. It's the years of smoking. Let's see if I can find the variable name. There it is. So I called it smoked underscore years. So this is my exposure variable. And then my model included income, race, sex, and education. Is that right? Let me just start at the top here. So here is the sex variable. So it is sex2 underscore 1. And then the next variable is race. And I have 4 dummy variables for race. I'm just going to grab them from here and take out the parts I don't need. So this, I need to get rid of this stuff here. So each variable name should have 1 space between it. There's no commas or anything like that. So we have sex, race, what's the next variable? Education. So I'm going to grab my 3 dummy variables for education here. And again, take out the parts that I don't need. So after education comes income, I believe, yes. And I have 2 dummy variables for income because I had 3 levels of income. And did I have any other covariate in my model? Years of smoking, age. Oh yes, I had age. And so age here is a continuous variable. This is in years. And then doesn't matter, uppercase and lowercase doesn't make any difference. Then I just have my outcomes, and that's it. So after the model, we put we have to put a couple of statements here. So what we want here is we have to put a slash here, and we want the model to calculate what are called confidence limits around the parameters. So we put CLPARM, that means to give confidence limits for the parameters. And then we have to write VADJUST, that's variance adjustment, equals none. We don't want a variance adjustment. So that's straight from the NHANES website. So this is longer than the line. So let me cut it into 2 lines. You can break it like this. It's no problem. As long as there's no semicolon here, it will continue reading to the next line until it finds a semicolon. So here we have the model. So I have FEV1. The exposure variable here is smoked years. Now, the exposure variable doesn't have to be in any particular order. I could put smoked years at the very end here, and it would work exactly the same. So there's no order here. I usually put it at the beginning just because it's easier to find in the output. But that doesn't really matter. So we are there. So we can run this model. So after all of this work to get to this point, we're actually ready to find out if there's an association between the number of years people smoked and the FEV1 to FVC ratio. Okay, so the moment of truth is finally here. Let's find out. What do we find? Okay, so here are the results. So let's take a closer look. So here we can see the results of our model. And if we scroll up here, we can see that these results are for the group where include underscore FEV1 equals 1. And we can see that the number of observations is 7,072. That's what we were expecting. Those were the number of individuals who were included in our model by this variable. And so when we look at the results here, down here, these are the estimated regression coefficients. These are the beta values in our model. And these were estimated using least squares estimation, as we discussed, because this is a linear regression model. And so here in this column labeled parameter, these are the different variables that are in our model. The intercept, this is our beta 0. This is the one that doesn't have any variable multiplied with it. Estimate, these are the actual beta values that the statistics program has chosen to orient our model to minimize the sum of the squares of the distances between our observed data points, the FEV1 to FVC ratios of each of the 7,000 plus people, and the structural part of our model. And these standard errors, these are an estimate of the amount of wobble that we have in the estimates. And then we have a p-value here, which is the probability greater than t. And so the p-value associated with the beta for smoked years here is less than 0.0001. So for example, if we were using a p-value of 0.05 as a cutoff for a statistically significant association, we are well below that for the association between the number of years that people smoked and their FEV1 to FVC ratio. And then what we get over here, this is a 95% confidence interval for the estimate, the beta value for the variable here, the smoked years. So we'll talk about that in a little bit more detail later. But let's first, let's write out, what does the model actually look like mathematically in detail that was estimated using our sample of 7,000 plus individuals. Well, the model outcome here is the FEV1 to FVC ratio, and we had a beta 0, and the beta 0 was estimated at 0.886. Let's use 3 decimal places here. 0.886. So it's 0.886. That's the beta 0. Plus a beta 1 value. That's what these smoked years. So the beta 1 value is minus 0.001. So minus 0.001. This is actually a minus here. Minus 0.001 times smoked years. And then the next variable was sex2 underscore 1. The beta coefficient was 0.018 plus 0.018. It's not a very good 8. Let me write that again. Times sex2 underscore 1. So I'm going to go ahead and write out the whole model. So once I write it out, I will turn this back on. Okay, here is our entire model. And you remember we created a model with undetermined beta parameters. We had a beta 0 here plus beta 1 times the number of years they smoked, plus beta 2 times their sex, plus beta 3 times the race dummy variable, the first or the second race category, and so on. And then we had an error at the end. This represents a random number that has a mean of 0 and a normal distribution. And so where do these numbers come from? Well, these numbers came from the statistics program. SAS estimated the values of these coefficients that would minimize the sum of the squares of errors between the data points and the model. And so you remember we looked at this image. And this represents a regression model. The pink plane is a regression model. The blue plane was what we were trying to estimate. And these red lines were the differences between the observed data points, each of these blue dots, and the model itself. And so what the model is doing, it is minimizing the sum of the squares of the distances between each data point and the model in the direction of the outcome variable. Now, of course, our model has many more dimensions than this model. This has an outcome variable. It has 2 variables on the right side of the equation. One presumably is an exposure variable. One variable is in there to control for confounding. Now, our model has many more variables. And so the dimensionality of our model is much larger than 3 dimensions. But because we can't visualize anything larger than 3 dimensions, we're using this as a kind of shorthand visual idea, a way to think about our model. So what should you be thinking when you see that this value of beta 1 is equal to minus 0.001? Well, what we are thinking about is we're thinking that if this was our x1 is our smoked years variable, then the smoked years is getting multiplied by that number, negative 0.001, which means that for every year that an individual smokes, their FEV1 to FVC ratio is decreasing by 0.001. And so what you can think is that there is a very slight downward slope in this regression plane. For every increase of 1, the regression plane is going down by 0.001. So it's very, very slightly different than 0. But if we think about our outcome, FEV1 to FVC ratio, remember that the cutoff for potential COPD was 70%, which would be 0.70. And the FEV1 can never be more than the FVC, because the FVC is a forced vital capacity. This is the total amount of air that you can blow out of your lungs. And the FEV1 is how much air you can blow out of your lungs in 1 second. And so the FEV1 is always going to be smaller than the FVC. And the range here is from about 0.50 to 0.99. So what would it mean if this was changing by 0.001? Well, it means that it would be going from 50% to 49.9, or from 70% to 69.9. So what this means is we have this beta coefficient, beta 1 times the number of years that you smoked, and the beta 1 is equal to negative 0.001. So what it means is that for every year that you smoke regularly, your FEV1 to FVC ratio decreases by 0.1%. So after 10 years of smoking, your FEV1 to FVC ratio would decrease by 1%. Now, this model actually isn't completed yet. There's more that we need to do to the model. We need to test some things about it to make sure that we selected the best model. But we're going to leave it here for now, and we're going to move now to the logistic regression model. Okay, for the logistic regression model, we're going to be using Proc Survey Logistic, and the strata cluster and weight variables are going to be the same. The domain now for me is going to be domain COPD. You might have only one include variable, but I have to use include COPD. And then the model, my model is going to be essentially the same, except that I need to change my outcome. And my outcome is going to be COPD is coded 1 for yes if they have COPD, at 0 if no. Now, for Proclogistic, you have to define which level is the event that you want to consider happening. So for me, it's like I want to model the odds of having COPD. And so I have to tell it that a value of 1 means that they have COPD. So I put event equals, and then I use single quotes and put the value in the middle. So it's going to be modeling the odds of a 1. The confidence limits for the parameters and the variance adjustment equals none is the same as in the survey reg procedure. And then I need to have a run here at the end. And that is how you set up Proc Survey Logistics. So it's very, very similar to Survey Rig. So let's go ahead and run this. I'm going to save this first. And let's see what the results look like. So here we have some results. So if we look at these results, if we scroll up, we will see that we're looking at the domain analysis for the include COPD equals 1. And the number of observations in this domain is 7,338. That's correct. That's what we had planned. And here we have the analysis of maximum likelihood estimates. Here is the beta 0, the intercept. The estimate is here. These are all of the variables in the model. These are the estimates for the beta values here. The p-values for the estimates are here, the probability greater than chi-squared for the logistic regression. This is the p-value. So if we were to look at this model with the regression coefficients in it, it would look like this. So here we can see the structural part of the model. Here's the beta naught, the beta 1, 2, 3, 4, 5, etc., multiplied by each of the variables. And so for each individual in the data set, their values for these variables will be plugged into this equation, and e to the result of that calculation would give the odds of COPD for that person. So the random event generator would generate either a 1 or a 0, COPD or not COPD, and the odds of the event, which would be COPD equals 1 or they have COPD, would be determined by the structural part of the model. So these estimates are a little bit difficult to understand intuitively just because of the structure of the model. And so there are another set of estimates that are given, which are the odds ratio estimates. And these are more intuitive. So here we can see the point estimate for the odds ratio associated with smoked years is 1.03. And what that means is that for every year that you smoke, your odds of having COPD is multiplied by this number. So if you have an odds of a particular value and then you smoke for 1 year, then your new odds are your original odds times 1.03. So another way to say that is that your odds of COPD are increasing by 3% each year, more specifically 3.4% each year. So we're going to be looking at this a little bit more later. And we also have more things we need to do to this model. We need to test some things to make sure that we've got the best model. But this is as far as we're going to go at this step. So your goal is to get your model to this level. You're running either survey, reg, if you have a continuous outcome, and you're running survey logistic if you have a binary outcome, and you are just putting your variables into your model as you have constructed them to this point. So your continuous variables will just have a single term, and all of your categorical variables on the right side of the equation, you will be using dummy variables. And you can use this syntax, and if you can get to that step, then that will be enough for this step in building the model.